in
Yes,
90.
I remember that. That was about 2 years ago.
Yeah,
No.
yeah. It's such
Yeah.
a. I mean, so many things have happened since then. Since then, because of COVID and all this, so it's quite a. It's quite something.
So here is Professor Carlos Modassores.
Yes, Professor Carlos. Nice to see
Hi,
you.
how are you?
Good, good.
So I muted the. Oh, it is recording right now.
Yeah. Yeah. I mean, it's okay, Jayan. You know,
That's
you
okay.
can just, as long as you don't say, as long as you don't say
Okay.
any impolitic things, we are okay. It's recorded for posterity. So if you want, you can pause it and start when the speaker starts.
I did put it on pause, but looks like it started again. Maybe
You can put it on pause. You can put it on pause. Whoever has control. So
okay, I'm putting it on pause. Okay.
yeah, there you go. I think it's better so that we only record.
Yeah.
When Dr. Lim starts. Otherwise, you have to get permission from everybody.
Right, right.
Siva, I will introduce you with just only one line because I want to give you the maximum opportunity to talk. So I will just say that anyway, Jayan is going to talk about your citation for the medal at the end of it. So when I introduce you, I'm just going to introduce you as professor from the Department of Architecture and Civil Engineering, City University of New York. I mean, City University of Hong Kong, and I'll give you the title, and then you continue.
Okay, sure.
Okay, and you have 40 minutes, including questions. So just if there are more questions, we'll ask them we'll have them put up in chat or we can ask them at the end of the meeting.
Great, great. I will have two parts, and perhaps the details I may have to go through quickly. So I will.
Yeah, I think that's okay. I think just keep. I mean, because.
It's important to give the big picture and more milestones of your work.
Yeah, and by the way, I'm very interested in this whole area because of my own interest in symplectic geometry. So I'm quite eager to hear your talk. So that's a good chance for me also. You. But
thank you.
I think especially because of the fact that we are doing it in Zoom, people get very zombie like too much, so that's why we are trying to keep it reasonably short, so otherwise people just lose focus. It's difficult.
Sure.
So that's the reason for saying keep it within 40 minutes, so that as it is, it's 2.5 hours of stuff, so it's quite a long time. Slowly people are coming in. That's good.
Is Professor Pauline not here now? I think so.
I'm not sure.
Yet.
I don't see him.
Still early in the US.
Yeah, it's still quite early in the US. It's 6:45, so he's probably gonna get a cup of coffee or something like that.
Hi, Aaron. Do you know whether the conference will take place at the end of the year? What do you expect?
Shiva he's muted.
Oh, muted. Okay.
Which conference you're talking about?
The MMS.
Oh, it will be in, of course, College Station, but we don't know the dates.
We don't know when. You mean I heard you? I heard you as where, not when. So we don't know when yet. But the plan is to have it in College Station. Most likely August. Most likely, but we don't know yet.
The best months, basically.
Yeah, the hottest part of Texas, unfortunately. But we don't know yet. I mean, no.
By then, I believe the population of people having vaccination should be sufficiently large.
Yeah. So, but the real issue is whether the college will allow, whether the university will allow.
Okay.
Because it's a the university still has restrictions on who can come and all that. So we are trying to see when that will go. So that is the story. Prakash, I think it's time for us to start.
Oh yeah, it's 1 more minute. Yeah.
Yeah. So I mean, we are waiting on the college to give some updates shortly, but it will be in College Station.
Sure.
So the recording has started.
Yes.
Thank you, Jan. We'll start promptly at 7.
Yeah. There's quite a few people who have joined. So
very nice.
That's
okay. I think we're good to start.
Yeah, I'm gonna please mute your mics so that there's no feedback.
Yeah. So good morning to all of you in the Americas. Good afternoon to all in Europe and Africa, and good evening to all in Asia and Australia. On behalf of Dr. Reddy, Dr. Srinivasa, my co-host, I, Prakash Tamaraja, Dr. C.W. Lim, and Dr. Glaucia Paulino, we would like to welcome all of you to this very special Reddy Zoom Medal event. It's a very special event. So before proceeding further, I would like to request to all other participants to switch off their microphones and videos in order to preserve bandwidth. After each seminar, we will allow a few questions for the speaker. Please list out your questions in the chat session along with your names. So just in case, if you get shut off during the question and answer, I can read the question to the speakers. So once I call your name, you may switch on your video and your microphone to ask your question to the speaker. Once the speaker has answered the questions, the asker may switch off his video and microphone again. So without further ado, I would like to welcome and introduce Dr. Reddy to give a few opening remarks. Jan? You're muted, Jan.
Very good morning to all of you, colleagues everywhere around the world. I'm very delighted to be here sharing these few moments. And it is very good to see many of you and recollecting where and when last time I met you. But it is unfortunate that I have not traveled in more than a year. But I'm hoping to travel in the coming months. That might be very optimistic, but I have my 2 doses of the vaccine, so should be able to travel. So welcome to the J.N. Reddy Medal plenary lectures as well as the award ceremony. And so a little bit of background of this medal. It was instituted by the journal Mechanics of Materials and Advanced Materials and Structures under the leadership of Professor Erasmo Carrera, who is the editor-in-chief, in honor of the founding editor-in-chief, that is me. So the award is given annually to known and well-accomplished researchers in the area of mechanics of materials and structures. And it is usually presented at the annual conference of the MEMS, Mechanics of Advanced Materials and Structures. Unfortunately, due to the COVID-19, we were not able to hold that in College Station in last October. So we postponed several times, but now we have not set the date until things are normal. Hopefully it would be in 6 months to 9 months period. So we did not want to delay this event because it is a yearly award, and it is the recipients are selected by an international committee of distinguished researchers and past recipients. And so this year we have selected 2 of them. And as you know those names, and we wanted them to give the plenary lectures, which would have been at the event, the actual conference, but now we preponed so that we can have this done, and we want to have them the medals received. So I leave this back to Prakash. Thank you again for attending this event.
Thank you so much, Jan. Very nice words indeed. So without further ado, I would like to introduce my co-host, Dr. Arun Srinivasa. Dr. Arun will be giving a brief biography of Dr. Lim before his presentation. Thank you, Arun.
Welcome to all. My name is Arun Srinivasa, and I've been. It's been my honor to be Dr. Reddy's colleague and I would say co-conspirator in a lot of research items along with Dr. Tamburaja. It's my honor to introduce Dr. C.W. Lim, who is the first of this year's recipients of the Reddy Medal. I want to give Dr. Lim maximum chance to talk, so I'm not going to do much of a biography because anyway, Dr. Reddy is going to talk about it at the medal ceremony. So Dr. Lim is professor of the Department of Architecture and Civil Engineering from the City University of Hong Kong, and he's going to speak on research frontiers in symplectic elasticity approach in mechanics and dynamics of seismic metamaterials. Dr. Lim, please, you should be able to present now, and I would like to hand it over to you. Thank you.
Thank you very much, Mr. Chairman. First of all, my appreciation, and also it's my honor to receive this medal. And I wish to thank the organizers, especially those who has put in so much effort in organizing and putting all of us together in a different dimension. We hope to be able to meet in person, but in fact, we are meeting online. This is the first, it's a quite unique experience. Okay, now of course, I treat Professor Reddy as my mentor, my friend, and also my collaborator in research. And I do appreciate especially by Professor Erasmo Carrera and also Professor Prakash Tamburaja. So without now let me share my presentation. Can you see my presentation?
Perfect. Thank you.
Wonderful.
Yes.
So now the topic that I wish to share with you is there are 2 parts. These are the works I have been focusing in the last few years, or perhaps the last 10 years and so. One of them is on symplectic elasticity, and the second one is on metamaterials. It could be I'm interested in low frequency metamaterials, including phononic and also seismic metamaterials. There are 2 parts here. The first, I want to because of time limitation, I want to go through the basic concepts and with a little bit of examples and the details. For details, perhaps you may refer to some of the references that I may show to you. The first part is on symplectic, as you may see, and the second part is on seismic and phononic metamaterials. Before we start, perhaps a little bit of Hong Kong and also CTU. In this picture, you will see that although you, hopefully after the pandemic, all of you will be able to visit Hong Kong again. We have the, this is a night scene of Hong Kong Victoria Harbour. And we have the very few beautiful and fantastic spectacular night scene at the Victoria Harbour. And this is a central. You can, oh no, this is a view from the center across to the Tsim Sha Tsui Park. And we do have a theme park, Ocean Park and Disney, and I think kids will enjoy. And a little bit about CTU. We are one of the few universities in Hong Kong. We do not have many universities, and we were one of the few. And we are pretty young, but we are very dynamic. And if you come to CTU, you will see that we are located. We are located in a not a big compound, but we are very dynamic. Our department of architecture and civil engineering, we have various different. We are interested in different fields, including construction management. We do have people doing structures. We do have people doing built environment and wind engineering, and also environmental and services. Now, back to my talk today. First of all, I wish to introduce to you a symplectic or symplecticity. Perhaps is a new term to many of you, but let me show you the background. In fact, symplecticity is a Greek word that means complex, and it was first introduced by Hermann Weyl, who was a mathematician and also a theoretical physicist in the early of the last century. And symplecticity is indeed in our engineering or our research. Meaning it means a concept of geometry is a different kind of geometry. And symplectic geometry is actually based on Hamiltonian system and canonical equations. And it was in the very beginning, it was used pretty much in theoretical physics and also in mathematics, whereby people mathematicians use the concept of a symplectic space to introduce manifolds, different kind of higher dimensional manifolds. But we engineers only started to use this concept in perhaps very much later. And in elasticity and solid mechanics, it was first introduced by, in solid mechanics in particular, it was by a group of researchers, including Professor Chong from China. Okay, symplectic solutions, what can it do? It actually applies the Hamiltonian principle. And we do use eigenvalues and eigenvectors to solve for many problems. Even if it is a static problem, we do use eigenvalue equation. It's different from other concepts like eigenvalue perhaps refers to vibration and also buckling, but in symplectic methodology, we use eigenvalue equations to solve even for bending problems. And the beauty of it is we do not need to do any trial functions, not like perhaps the semi-inverse method by many people such as Timoshenko or Neville solution, Levy solution. They used to start with some trial functions, but we do not. And we follow a step-by-step derivation procedure, and we will ensure that we will get the solution. So a bit of history. In symplectic method in mechanics only, I'm not talking about theoretical physics and also mathematics, but I'm talking about symplectic geometry in mechanics. The first piece of work, it was in 1956, but unfortunately, due to some reason, it was unpublished, and the work was only known very much later. And the first published, it was due to Vogler and in 1956. And the first published work for symplectic method in mechanics, it is actually, when it was first started, it was actually a symplectic integration. It was used for numerical analysis, and it was published in 1983 by Ruth and later by Chenner, and subsequently it was published. The most serious work in symplectic numerical methods was published by Feng Kang in China in 1955. He started seriously in this area, and he published a number of very good methods for symplectic numerical analysis. However, the first piece of work which applies a symplectic method in solid mechanics, but not for numerical analysis, but for using symplectic method for solid mechanics, deriving exact analytical solutions, was due to Professor Chong in Dalian University is in China. And subsequently, I have been fortunate to collaborate with Professor Chong and his group of researchers in Dalian University of Technology in this area in symplectic method in elasticity. You may see that indeed, the first few pioneers in symplectic numerical methods has actually made a very good progress, or has been doing much work in this area. And the piece of work was actually recognized in one of the books by Harrer in 2006. And I have been fortunate to write a book. The first piece in English. It was actually there was actually a translation from a Chinese book, and I have been in fact very fortunate to publish the first piece of English work in this area, symplectic elasticity, and it was once one of the best-selling titles in engineering mechanics during the when it was first published. Okay, now let me introduce the concept of what can it do. Now, first in symplectic geometry, we actually introduce a 2n dimensional space. We have to build we have to introduce one n-dimensional linear space and another linear dimensional space, and we introduce two vectors. These two vectors, two of them put in together to form a 2n linear dimensions. I will talk about it more later. Well, like many other geometries, Euclidean space or other mathematical space, in this symplectic space, we do have some rules. We have to obey some mathematical rules. The mathematical rules is, if we have an inner product of two vectors of it, when we reverse commutative, then it becomes, we have to include a negative. So it is when we have a multiplier, we can actually take the multiplier. So this symbol of a bracket is actually what we call the inner product. Okay, so for this is a commutative law. This is a associative law, and this is a distributive law. And we do have also one other law, which when one of them is 0, then the product or the inner product is also 0. The inner product is defined. This inner product of two vectors in symplectic space is defined as a multiplication of the element of the first vector to the corresponding element of the other second vector, and then minus the other way around. So in short, it is given by this definition. We do also have a unit matrix in symplectic space. So the unit matrix is actually a composition of the what we are what we know very much about this is that unit matrix in our common mathematics. So let me take a 2D symplectic space. For example, when we do an inner product of a 2D 2D symplectic space is actually representing an area. So the inner product of two vectors in a 2D symplectic space actually imply the area of that geometry. Okay, so we do also have a orthogonality when we apply two vectors, two inner product of two vectors in a symplectic manner, which is 0, we call them orthogonal. And we also have a symplectic join. So this is the symplectic orthonormal vector set of vector set, and that satisfies this relation. So if you are interested in the details, perhaps you can refer to the book on symplectic elasticity. You may find it on internet. All right, the symplectic matrix has some properties. When we do have a symplectic matrix S, which is a 2m by 2m matrix satisfying this condition, then the inverse matrix of a symplectic matrix is itself another symplectic matrix. The transpose of the matrix is also a symplectic matrix. The determinant of a symplectic matrix is either equal to 1 or -1. The product of the symplectic matrix is itself another symplectic matrix. So this is so if we have a Hamiltonian matrix H, which is a 2m by 2m matrix, then by having the inner product of that matrix, we do get this one. So these are the properties of which I will go. I will not. Perhaps I have to go a little bit faster on it. So if we have an eigenvalue mu of that Hamiltonian matrix, then minus mu is also an eigenvalue of that matrix. And if 0 is an eigenvalue of a Hamiltonian matrix, then the multiplicity is always even. All right, now it is more interesting here. I'm going to tell you the correlation between a Euclidean space, which we know very much, with the symplectic space. As I told you just now, the inner product of two vectors in the Euclidean space is a length, but the inner product in the symplectic methods implies the area. So in this Euclidean space, we have the unit vector I, but in simplex space, we have J. And we do have orthogonality relation. In symplexics, we do have the same thing, but in a different definition. And orthogonality matrix, transformation, and symplectic matrix. And we do have eigenvalue and real eigenvalues relations between these two symplectic space and the Euclidean space and the symplectic space. Okay, now let me go on. How do we apply the symplectic method for solving solid mechanics problems? So first of all, we have to apply the Hamiltonian principle. We have to form the Hamiltonian canonical equations. So I think this part of you are very familiar. First of all, if we have an action A, according to the Hamilton's principle, which acts from a point T0 to TE, then the variation of that action, if we want to achieve the best, the nature of that problem, we always have the variation 0. So in so doing, we arrive the more famous Lagrange equation. So this is a Lagrange equation that now, using the Lagrange equation, we can form the Hamiltonian canonical equation. So deriving, if we have a generalized velocity q dot, which is then we can obtain the generalized momentum by having the partial derivative of this Lagrange function with respect to that velocity vector. So in so doing, after getting P, we can form a Hamiltonian function. Then subsequently, by using these two equations, these two relations, we can form the Hamiltonian canonical equations. This is very important because we need these two vectors, P and Q. We need these two quantities. The two vectors, one is a P vector, the other one is a Q vector, to form the state vector for the symplectic method, which we will apply very much in the symplectic methodology in solid mechanics. So now, I just want to show you one very classical problem of plate bending. We use how can we use a symplectic method for solving the plate problems? So we do have this a plate bending problem, the very common classical plate bond. So the key idea now is using that Hamiltonian principle, we have to treat the time coordinate as the spatial coordinate. Because for plate bending, it is not dynamic problem, it is just a static problem. So we don't have the time variable. So using the Hamiltonian equation, we use we treat the t time as the spatial coordinate. And then we have another spatial coordinate y. So in that case, x comes from time, the y itself is a space. So then we have to form a strain energy density, and we have the curvature. In this case, it is the strain energy density is expressed in terms of curvature, x, y, and also the twisting curvature. After that, we use a variational principle. By using the variational principle, we obtain the one of the Gaussian equation, also the boundary conditions. But here, as I mentioned previously, using the symplectic method and using the Hamiltonian canonical equations, we obtain this state space. In this case, this part, one of them is actually Q, the other one is P. So these two are vectors that form the state vector in the symplectic approach. In this case, this phi x and phi y are actually, this is phi, sorry for a mistake. So this is actually what we call the bending moment function, which is a new concept. And the bending moment function is related to the bending moment my, and this is phi y is related to mx, and also we have the twisting moment relation. Now again, we have to make another correlation between plane elasticity and the plate bending problem, because the plane elasticity problem do have a standard procedure of solving, but for using the symplectic method solving the plate problem, we don't have it. So we have to make a correlation between these two so that we can achieve the exact solution by using our experience in this plane elasticity problem. So in this case, we will treat the bend. We correlate we correlate the bending moment function with the displacement vector. And in this case, we have the strain energy, but in this case, we have the bending moment. So by using one-to-one analogy or correlation and using our knowledge in solving this plane elasticity problem, we do arrive the symplectic approach for an analytical solution by using the symplectic approach. That means, in short, we learn from the method of solving plane elasticity problem, and we borrow the method and we apply the symplectic approach. Using this experience of this model, we obtain an analogy or the correlation for symplectic bending problems. So if we can get exact solutions for plane elasticity, so we can also obtain analytical exact solutions for symplectic bending, and for any type of boundary conditions. For those who work on plate problems, we know that we can only obtain exact solutions for certain types of boundary conditions. But using this symplectic approach, it is very general when we can solve for any type of boundary conditions, which I will show you later, a couple examples. So in this part, I will go through a little bit quickly. So we will form using the Hamiltonian problem, Hamiltonian dual equations, we form a eigenvalue problem. So that's why I say that using the symplectic approach, even though it is a bending problem, we arrive at an eigenvalue equations. Okay, so this is the state state vector which is formed from the canonical equation. So we, in getting this state vector, we have to apply the symplectic concept. So this state vector forms from this vector and also this vector. So there are two vectors Q and P, which can be obtained from the Hamiltonian canonical equation. So, so if we can, so let me go back. If we can solve this problem, of course, we can solve this problem, then if we can solve problem, that means we can solve the analytical solutions for this state vector. Then by integrating, we know that this is a curvature, and by integrating this solution, we can obtain the deflection for a plate. So this is a solution problem. I think I will go through a little bit quickly. So first of all, we apply the separation principle. We separate the two variables, and if we substitute this into the equation, the previous eigenvalue equation, then we obtain this and not this eigenvalue equation. Then subsequently, we obtain a general solution, and we have 1, 2, 3, 4, and these unknown constants can be obtained from the boundary conditions as usual. Substituting, then we substitute the general solution into the corresponding boundary conditions on both sides. We can obtain the methods by eigenvalue and eigenvector expansion. So now, one of the examples, in this case, let me assume simply supported first. It can be any boundary condition, but let me assume simply supported. We have the moment equal to 0 and also the deflection equal to 0 on both two of the opposite sides. The other two sides we don't care. But in symplectic method, we don't deal with MW. We deal with the bending moment function. So we have to find, and we have to convert this boundary condition to the bending moment boundary conditions. So in so doing, we obtain two of the boundary corresponding equivalent boundary conditions. After that, we solve for the by substituting and getting the determinant of the matrix equal to 0. We can obtain this we use a transcendental equation like this, and also the eigenvalue and eigenvector of the 0 order. Then we can, if we substitute, if that form is a Jordan form eigensolution, then we have to also find the first order. So by using the standard method of the Jordan form eigensolution, we can obtain the first order eigenvector and also the first order eigenvector, and we can obtain the first order of the state space. So by integrating this state vector, we can obtain the deflection, and this is our ultimate aim. After that, we compose, or we combine the 0 order and the first order, and then we use this expansion method. We can obtain the solution for the state vector, and by integrating this state vector, we obtain the deflection. But now, bear in mind that doing so, we only obtain this part. We have another part. This part should be obtained, to be solved from the particular solution. This is only the general or the complementary solution, and we do have another particular solution, and this particular solution should be obtained from the loading. So now, if we consider opposite sides simply supported, I go quickly, and then we obtain a particular solution in this form, and after that, we obtain the curvature and the bending moment. Now, if we further apply, just now we only apply two of the boundary conditions. We have another two different boundary conditions. Then for a fully simply supported plate, we have a further two boundary conditions, and apply these two boundary conditions, we obtain this exact solution. This exact solution is not new, because we know that fully simply supported plate the exact solution is available. So we are just repeating others' work. But no, now from this part, if we deal with other boundary conditions, we obtain a different or exact solution. That means we apply the rational procedure to other types of boundary conditions, we can obtain the exact solutions. So this exact solution is again new because for opposite sides simply supported, the exact solution is available. But what I want to show you is we can use the same method to solve problems where the exact solution is not available. So this is a case. In this case, if we have a so in this case, this is also exact solution is also available by using the Levy method. So I don't want to talk about it. I want to show you another case, which is a corner supported. Okay, so in this case, 4 of the points, this is corner supported. 4 of the points are corner supported. So in this case, there is no exact solution available. But when we apply the simplex method and apply the boundary conditions, we can actually derive the exact solution. Or in fact, this is to be in a serial form of exact solution. So now, if I compare with the finite element solution, which I want to tell you is, now using this corner support, there is no exact solution available, but there is an exact solution on only one particular point at the corner. If at the corner, we can get an exact solution, which is equal to 1/8. The twisting moment is equal to 1/8, but this exact solution is only at one particular point. So if we use our symplectic method, we obtain as 0.12, nearly very close to the area. Because what the area is because in our symplectic solution, it is actually a serial form. If I can actually include more and more terms, and this value would be approaching 1/8. However, if we use a finite element, you may see that the twisting moment is very far out. So this is the beauty of the simplex method, that we can actually solve problems that the classical method or the semi-inverse method can never achieve. Now, I have actually applied this symplectic method for different cases. For Timoshenko beam, the state vector is actually a product of displacement with the rotation, and another vector of shear force and bending moment. And for plane elasticity, we have displacement and stress. And for sectoral plane elasticity, we do have the displacement and stress. And for plate bending, we have the bending moment function and the curvature. And for piezoelectric beam, because in piezoelectric, we have to consider electric function. So we do have this vector. This is a vector Q and another vector P. So this is a displacement plus electrical potential, and we do have the stress plus the electric displacement. Now, the concluding is this approach is beyond the semi-inverse Timoshenko-like. We can actually go solve problems that the semi-inverse method cannot, because we do not need any trial functions, and we can actually solve for benchmark exact bending problems for opposite sides non-simply supported. In fact, indeed, is for any kind of boundary conditions. So let me go to the second part. I think I have to go through quite quickly. So in this case, this is about phononic crystals. In this part, in the phononic metamaterial is actually not a natural material. It's actually a man-made design. So we design we use the material to design with a certain configuration such that we can achieve, or in the overall sense, we can achieve some global properties which simple natural materials cannot achieve. For instance, we can achieve the negative refractive index. We can actually propagate wave in a in any manner that we like. It's a waveguide. Bear in mind that in this case, the wave can actually bend. The wave can make a corner without reflection. This is not reflection. It's not like placing a mirror here and let the wave reflect. No, because by placing a mirror here, actually there is a reflection and energy will lost somehow by absorption or by dissipation. But in this case, the bending of this wave is 100%. It is actually by resonance, by the resonance of the structures. So in electricity and electromagnetic, so we can have the permittivity and the permeability, which is when it is one of them is zero or one is negative, we can actually control the electromagnetic wave. Oh, sorry. And for actually these metamaterials actually can be found in nature by not natural elements, but it can be found in natural beings like a bug or like a butterfly. Actually, they are some parts of the body are composed of metamaterials. Metamaterials can also be used to guide wave, and for this power splitter and waveguide, and I can actually also use to protect civil structures. And this is what I wish to show with you. And some of the work that I've done, that our objective of using this resonance is we can build constructive interference. In that case, it will be a passband. A passband is not good. We don't want that. However, if we can make use of this destructive interference, then we will achieve a band gap. So having a band gap, wave cannot propagate through, and somehow some part of some region of it will be protected, and wave will never be able to penetrate. And having a particular point which is a passband, then we can actually guide the wave using that particular point or the particular path whereby wave can pass and the other parts wave cannot cross. For instance, in this case, this part of the building is protected. If let's say we have a seismic wave generator here, if we have a seismic metamaterials around this building here, this part of the building is protected. Now we can also guide wave by having by designing the pillars in a specific manner. We can actually guide the wave through a path that we want. So, and in this case, it is what we call a topological protected interface mode. In that case, what happens is we can divide an area into two different, or a few, not necessarily two, even a few different regions, whereby there is a boundary between two different designs. Okay, so then by so doing, there is we can design that such that these two regions wave are regions of a band gap that wave cannot penetrate. However, at the interface, there is a protected, topological protected interface mode, whereby phase can only go through at the interface. Therefore, we can design the interface in such a way that wave can only go through that particular path, and this is what we want. So in this case, our interface is a straight line. However, we can actually design the interface of this. This is a design, and this is a different design, and we separate this different design with a zigzag path, and therefore wave cannot go anywhere. They must go through the path that we design for them. This, bear in mind again that this is not reflection. There is no wave reflection. It is actually due to the wave propagate actually due to resonance. And okay, in fact, indeed, we can actually control the spacing. These are the different design. We can control the spacing. We can control the size. We can control the distance from the center. This is a unit cell. There are a lot of parameters, geometric parameters or material parameters that we can control, such that we want to achieve a wide band gap. So we want to achieve a wide band gap. as large as possible, such that we can manipulate what we want. So if for those who do classical vibration, we know that if we have we do free vibration, no damping, we can actually get different modes whereby the two frequency cross. However, if we introduce a little bit of damping, these two curves will separate. So actually using damping is a way of a concept in metamaterials. In metamaterials, we can also use damping to separate the wave, such the two modes, we separate the two modes such that in between there's a gap. And this is a gap that we want to manipulate. So this is a work that we recently published, and you can see that we are able to achieve a wave path or a waveguide that we want in a zigzag manner. And indeed, this is zigzag manner is just for manipulation. We can design in a 3D manner, 2D manner, and to achieve a path that we want. Okay, so I think I have to go through a little bit faster. And in this case, we also consider the surface effect. So by having the surface effect, we can actually move so our surface effect is only available when the size is very small. So in this case, the size is at perhaps at oh no, sorry, this is not surface. This is using the piezoelectric and piezoelectric or the boundary conditions using the different electrical components to control unsymmetry about capacitance to achieve a negative. This is a negative capacitance, which you cannot find in nature, but we use a special design to achieve negative capacitance such that we can control the wave frequency response. And this is another case of a topological protected interface mode. In this case, we want to achieve, we use the different design, whether it's a circular or
excuse me, Dr. Lim, you have about 5 more minutes to wrap up your presentation.
Sure, sorry for that. Then in this case, this is another, we use a active controller. We can also use electrical active control to control the band gap in metamaterials. And again, we use some mass in mass, spring and mass to design some unit cell, and we can have a single unit cell, a double mass system unit cell. In that case, we can again control the band gap. Now, go for seismic metamaterials. You can see that in this case, if we have the metamaterials built, an area that we want to protect, when there is a wave, activation of seismic wave, you can see that the wave will be changed into the butt waves. The surface wave will go through into the deep into the ground, becomes you can see that it becomes a butt wave, so that this type of a structure will be protected. In that case, again, I work with my students and we design some structures, and we may use these structures around the building, such that when there is a Reddy wave moving here, the wave will be reflected deep into the ground as the butt wave. And again, we analyze this structure using numerical methods. We will be able to identify the band gap. The gray area part is indeed the band gap. So these are all the pass band, and this is a band. So we want to have this portion or this region of the as the area to be protected. So now let me show you one of the examples. We have a metal barrier here. This is our design. We put a probe here before and after, and if there's an excitation here, what happened to it? You may see that a low frequency before the metal barrier, there is a wave. After passing through the metal barrier, the wave will be reflected to the ground. So this is what we want to achieve. So we sweep across from the 9.5 frequency, 9.5 hertz to 18 hertz. We achieve a good result. So this is actually a space, an analysis of the, and in this case, you can see that in this part, is actually where the meta barrier is located. So when there's a wave, where there's the incoming wave, after the meta barrier, the response is very low. So now you may see this is an animation. So in this case, this is a meta barrier, and where the wave will go deep into the ground. Sorry for that. Okay, so this is another example of it. Seismic materials, and this is a analytical model. And if you are interested, you may refer to my paper.
Can you please, somebody, can you please mute your mic, please?
So again, this one shows a flow gate block periodicity condition. And we do have actually achieved a big band gap using the meta barrier. And finally, another example of using different design, sweeping from a low frequency 3.5 to 20 Hertz, we can identify which part the design is the best. And this is again another spatial
2 more minutes,
analysis.
yeah?
And analysis of the band gap. We may change the material properties, we can change the geometry properties in order to optimize the design. And again, this is the frequency response for different geometry properties, height and width. And indeed, we can also change the spacing of the meta barrier. And actually, in fact, I forgot to tell, we can treat this one as the natural tree. So forests can itself be a natural metamaterial. So this itself can be trees, and we can actually treat forests as a natural metamaterial. So this is a animation of the seismic metamaterials, and the conclusion now is forestation is found actually an effective, sustainable approach to mitigate ground-borne vibration and seismic waves to ensure protection of civil infrastructures. So what I want to highlight is we can use man-made metamaterials, and we can also use natural forestation, and we can actually plant trees in the way we want in order to achieve. So in so doing, we can actually gain also control on climate change, carbon footprint, flood resistance, fresh air, and sustainable environment. We can actually achieve protection as well as environmental, not only civil structure protection, but also environmental protection. So there are some, of course, there are some limitations and recommendations. I wouldn't want to go through it one by one, but you can find it in my paper. And lastly, I wish to make acknowledgement to my group of researchers. This group of researchers from Dalian University of Sydney, especially Professor Shi. I work with them in symplectic method. I learned from Professor Chong, and also I have a fortunate to work with them, and we learn from each other. And also, I must pay tribute to my students who work with me in metamaterials. So I have two different groups of collaborators. The first group on symplectic elasticity, and the second group, which is on metamaterials. And finally, last but not least, I wish to thank my family, my beloved wife, and my two kids. And without their support, I would not have achieved what I have had today. Thank you very much.
Thank you, Dr. Lim, for a very nice presentation. So I'll open the floor for questions. Yeah, the first question is from Dr. Glaucio Paulina. Glaucio, would you like to unmute yourself and ask the questions?
Prakash, you might as well just.
Yeah, sure. I can ask the question. Yeah, sure.
Yeah.
So, Dr. Lim, thank you. This is a question from Dr. Paulino. Yeah. So his question is, do you use any experimental results to validate the topologically protected states?
Very good. Very good. Very good question. There have been experiments done by others. We, because of a laboratory equipment limitation, I do not. But we do have experiments working on some phononic crystals, but not not the topological protected interface mode, but we do have design which we have published recently in a different paper. I did not show you here, on phononic and also acoustic metamaterials, whereby we are able to achieve the frequency response and also the bandgap that we want. It is actually it's actually not too difficult. It's actually mass with spring, and we actually tested in the lab. And the work is actually ongoing, and we hope to publish a work very soon. Thank you very much.
Thank you. And the next question is from Dr. Arun Srinivasa. Arun, would you like to ask your question personally?
I had a question, and this is actually related to the next question also on chat that I could see, which is, Dr. Lim, I saw that you did a lot of analytical solutions which were for using the symplectic approach. Have you developed numerical techniques based on symplectic approach? And and I had the same question as the next questioner, which is, if you have, how is the convergence compared to traditional approaches, and where are the I would say advantages?
Okay, thank you. Thank you very much. Symplectic method, as in the very beginning, symplectic method was borrowed or was applied from physicists to actually numerical methods. So there is actually a group of people who works on symplectic numerical integration. That is a branch.
Yeah.
So I don't do it by using this. What I know is using the symplectic integration, the energy is conserved. Therefore, even though if you run a numerical iteration for thousands and millions of times, if you use a normal numerical method, the error will accumulate and then you will diverse. If you have millions and millions of iteration, after many millions of iteration, the error accumulate and it will diverse. But if you use symplectic numerical integration, because every step we have to ensure symplectic conservation. Symplectic actually is related to energy conservation, and therefore, if you use symplectic numerical integration, the error is actually controlled. We can control the error, and after many hundreds of millions of times, the numerical result is, we can ensure accuracy of the numerical result. However, I don't do it that. We do it symplectic method in analytical solution, but not numerical solution. So question is, how accurate is my solution of that approach? When we use symplectic method for deriving analytical solution, our analytical solution is in fact a series. So we don't need a very rigorous numerical method to solve the integration problem. We actually solve the series. We just input value, and I can obtain the result just by pressing the button. So I can include 5 terms, 10 terms. So the more terms I include, the better the result. So indeed, we can actually achieve as high accuracy as I want by including more and more terms. It's actually no need numerical. It's just substituting and obtaining solution. It's not doing numerical analysis, repeating and repeating.
Yeah, got it.
We don't do that. We don't do that.
Thank you.
Thank you, Dr. Lim. And a final question, before we move to the next speaker. So a question from Hua Li from NTU Singapore. How about dimensional analysis of symplectic elastic methods?
Dimensional analysis.
Yes.
Sorry. Okay. Let me explain what's my question. Sorry.
Okay, thank you.
Okay.
Dr.
Thank you so much, Professor Lina. So beautiful work. Okay. Can you remember you present one slide showed the comparison difference of 2 systems, right? One is the Eulerian system with the unit as length. Then you start from the area, right? So means that your system with some unit, right? Do you remember when you explain what's meaning syntactic method? You make a comparison between the Euleric system. X, Y represent length. You are represent. Do you remember the table?
Okay.
Yeah. So this, but I check, I follow the formula, but no much difference compared with the classical one. So how to understand? Suppose the suppose the form of energy represented by different form, right? Can I say that? Because you are unit different. You get my point?
I
Go
got
back,
your
go
point.
back. You go back long, maybe very beginning when you do introduction, very fast. One table, just compare. No,
This
no,
one?
no, 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 no. Go, 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 go. Yeah, yes, here. Yeah, no, no, no.
Okay.
Yeah,
Yes.
you say that internal product in the electric, right? It's the length, but here is the area. So means the unit different. Can I say different unit? Can I say that?
Yes. Yes.
So different units supposed but energy is supposed to represent by different form. Can I say that?
No, the energy, because we use a Hamiltonian principle, the energy expression is used the same energy, because we are still apply Hamiltonian principle. The main
So means
view,
can I understand this way and in this way, because energy is the scalar, is no vector. Can I understand this way? So it's the same.
okay, yes, energy is a scalar. That's correct.
No, my question is my understanding correct? Because the two space have the same form for energy. The reason is the energy is scalar, no vector. Then otherwise it's support different form, right?
No, I don't know whether I get your answer.
Yeah. So
I think,
in the interest of time,
yeah.
can we move the discussion to the end of the next talk, because I want to make sure that Dr. Paulino has full time to present his stuff. So I would like to move on to Dr. Paulino. Thank you very much, Dr. Lin.
Thank you very much, Dr.
Dr.
Lim.
Lin. I'm sorry, but we have to. I mean, given the limitations of time, we have to do.
8 o'clock is our next target.
Yes. Our next speaker. It is my great honor to introduce our second recipient of the J. N. Reddy Medal this year, Dr. Glaucio Paulino. He is the Raymond Allen Jones Chair, Department of Civil and Environmental Engineering, Georgia Institute of Technology. His talk is entitled Origami Engineered Metamaterials and Robots. I would like to give him maximum time. That's why I'm not introducing more, so that Dr. Reddy can actually talk more about their contributions and so on. Dr. Paulino, you are on. Please take over and present.
Thank you.
Yeah. Yes, we are able to see.
Perfect.
Thank you.
Is it okay?
Yes.
It's good.
All right. Thank you very much. Well, thanks, JN. Thanks, Arun. Thanks to all the organizers. It is a great pleasure to be here today. I really enjoyed the talk by Dr. Lim, and I received the Reddy medal that is in here. I also received the certificate, very beautiful, and I am very happy to be here, and especially considering that JN is such a special person in many different dimensions for me. For example, when I first learned finite elements, I learned from his book in the late 80s. So I am going to talk about origami engineered metamaterials, structures, and robots. And before I go on, I have some acknowledgements to make to the students and collaborators, Evgeny Filipov, Tomohiro Tashi, Horacio Espinosa, Sirida Krishnasamy, Renee Zhao, Kelil, Chris, Pradeep Pratapa, Larissa Novellino, Shizeze, Shuai Hu, Heimin Wei, Nicholas Alderet, and Zhao Wen Lin, and Professor Renee Zhao from Ohio State University, I think I mentioned. And the sponsors from this work, the National Science Foundation, the JSPS, and the Raymond Allen Jones Chair. And also to JN, because as I indicated, I learn finite elements from his book. And if I may, what I would like to do, and I hope I will do this just was
那个
put
所有东西啊都发给我，因为那个表啊，我还要加几句话。
Can you please mute those of you who are not presenting, please? Thank you.
Okay, can you see my screen?
Yes.
All right, and this is part of the introduction, JN, because I work with origami, and origami has a very good connection with art, and I wanted to make a connection here. And then this is a code that we wrote. And the code is running. This is the MATLAB screen, is only 30 iterations. This is the finite element mesh. And now, let's see.
Ah, wow. That's very nice.
Last year, it has more hair than I do now.
Yeah,
That is beautiful. That is beautiful.
Oh, thank you, Arun. I had some problem. I prepared the full screen, but this is supposed is an artistic representation. And if you step far away, it looks more like a photo. If you are closer, then this looks more artistic. So, and maybe I will stop sharing this one. And,
That was very nice. That was very nice.
thank you. And I will share this one. Okay. So in my talk, I will give a brief introduction about origami engineering and math. Then I will talk about the Odyssey program. This is a program that we had at NSF when I worked there. And is a program on origami design for integration of self-assembly systems for engineering innovation. And then I will talk about the Merlin software. Is a structural analysis of origami software that is very simplified, but allows you to do the origami simulation very fast, to consider the nonlinear mechanics of a non-rigid origami. Then I will talk about tubes, and especially the zipper couple tubes. And here is a zipper couple tube. As you can see, this is a big one. And then what can we do with these tubes? Maybe some configurational metamaterials and cellular assemblages, not just at the large scale, but maybe at the micro and nano scales. And then I will conclude with origami robots with distributed actuation and conclude the talk. Origami has been used as art, entertainment, fashion, education. It's a very pervasive topic. In the interest of time, I'll just show you, this is one of my favorite pieces of art in origami. It's fascinating. The orchestra by Eric Joazel. It has 11 musicians and 11 instruments and only 22 pieces of paper. This is of tremendous beauty and elegance. And here is one of the most complex origami that exists, the dragon model by Satoshi Kamiya. And when we talk about engineering applications of origami, then some of the words that come in mind is compact, deployable, prefabricated, self-assembly, tunable, multifunctional, adaptable. And here are several examples and references. And when we talk about origami, we have to, let's see if this video can. Okay. When we talk about origami, then we have to make considerations for theory and analysis, for design, how to design the system that we want to go from 2D to 3D, thickness considerations that may be an issue, and also talk about materials and fabrication. Okay, regarding the EFRI program, I worked at NSF from 2009 to 11, and during that time we created, me and other colleagues, the Odyssey program, Origami Design for Integration of Self-Assembly Systems for Engineering Innovation. And this consisted to use mathematics plus artistic inspiration, concepts from design theory, active materials to do origami and adaptive morphing systems. And some of the main themes were compliant mechanisms, active materials, bio-origami, foldable structures, and microstructures. This program supported about 13 teams in the country, a little bit more than 2 million, more or less. Each team was about $30 million of research in the field. And since that time, this sparked a lot of research in origami engineering, including my own. And let's start to talk about some of the mathematical rules of origami. One of them is if I want the system to be flat foldable, for example, like what we have in the center, it should be colored with two colors. This is a theorem that guarantees that. And then I have to satisfy the Maekawa theorem, the Kawasaki theorem, and the folds cannot interpenetrate each other. And these simple rules, they are quite amazing because many times, even for example, in different fields like quantum mechanics, you have a few sets of rules, but they govern a lot of phenomena. And similarly in origami, and these same rules can lead to the engineering innovation. Here, a few more details about the two colorability. What we notice is that in this system, the degrees of each vertex, they are even. And then, for example, if you, this is the crease pattern colored with two colors for the crane. And then when I fold it, you see what the property that I get is very nice. And then I have my Maekawa theorem that says that the difference between mountains and valleys in a vertex is 2 and only 2, no more, no less. Kawasaki theorem is one of the most powerful theorems that says that around the vertex, all the odd angles, they add to 180 degrees, and the same thing for the even angles. And this also guarantees developability. And here is the non-interpenetration condition. We also use some of these ideas to create a class at Georgia Tech in origami engineering. And this has been fun teaching this class. We have students from many colleges, about 5 colleges, many different departments. And has been very nice. One of the ideas, for example, is to use Legos to see how the origami works. For example, here is a Lego system that is showing a Miura, for example. Right? And here is Larissa showing how, for example, illustrating the use of an origami tube, for example. Okay, and at the end of the semester, the students do projects that are related to their interest, and this goes, in general, I have lots of students from bioengineering, biomedical, and then this goes from that area, like you can see here, the cast gummy, to space exploration, like self-cleaning solar arrays, and many things in between. So let's talk here about origami then. The most, maybe the most famous developable pattern, I think, is the Miura. And the most famous non-developable is the egg box that we can see there. What happened is, if we look at the Poisson ratio of the Miura in plane is negative. If you shrink in one direction, you shrink in all the directions, but it's positive out of plane. When you bend it, you can see that they form a saddle configuration. The egg box is exactly the opposite, because the egg box in plane is like any regular material, has a positive Poisson ratio, but out of plane is negative, as you can see, and it forms like a dome. But you can see that Miura is Miura, egg box and egg box. You can see that, right? They are different, right? Miura is Miura, egg box is egg box. What about if we could develop a metamaterial that has all these properties together in the same system. Wouldn't that be nice? And that is something that I will motivate a little bit later. And one aspect I would like to mention very briefly is that the origami has a tremendous beauty on it, embedded. It is natural. Many times has tremendous symmetries, has tremendous patterns. It's very beautiful. And this beauty in the geometry, it also translates into the beauty in the mathematics and the mechanics. And I hope that I can illustrate some of that for the remainder of my talk. For example, regarding the mathematics, the group in Harvard, by Wei et al., they did very sophisticated calculations to show analytically that for the Miura, the Poisson ratio in bending is given by this expression, where the notation is given here on the left, and in stretch is given by the expression below. If you compare the two, the only difference is a sign difference, that the Poisson ratio in bending is the negative of the one in stretch. Later, Nassar and the colleagues did similar calculations for the egg box, and they found the same geometrical mathematical relation. And recently, we wrote a paper in PRL on geometric mechanics of origami patterns exhibiting Poisson's ratio switch by breaking mountain and valley assignment. And we did the mathematical derivation for the Poisson ratio for this new material pattern that essentially includes the properties of both the Miura and the egg box. And we found the same beautiful relationship. And then we also found that these previous cases in the literature, like these ones, they just become particular cases of our general derivation. I will not have time to go into the details here, but all the details are shown here in this paper. And if you have any question or any follow-up, I'll be more than happy to talk to you. And I'll just show you some of the things that we can do with this pattern. And the key idea is that it combines the properties of both Miura and egg box. What can you do with this? For example, metamaterials. And I have, the sky is the limit. I can do it in many different ways. And for example, here I can choose the unit that I want. On the left, I put all Miura, on the right, all egg box. And then just to illustrate to you what happened, if I bend this, then you can see that the right bends like the egg box and the left bends like the Miura. You have a negative Poisson ratio here in bending on the right, and a negative one, the saddle type configuration on the left. But this is the same material. You just activate the mold by means of kinematic applications, for example. And here is another one, and I can do this in many different ways. Here I alternate egg box and Miura modes. And then I get this metamaterial, and then if I bend them, then you can see that I get more a dome type configuration, and that makes sense. So moving on, I want to talk about tubes. Now, how we do tubes. I pick up one Miura strip and put it together with another one. I form a tube. And I can look at the rigid folding, but I am also very interested in the elastic deformations. And that's an area that is very good for mechanicians because I think there is a lot of the mechanics to be explored in the field of origami, a lot. So what we have been looking is the elastic modeling, and we are thinking in developing a simplified model that would consider, for example, that would be very fast, efficient. Because if I try to use, well, JN has developed one of some of the best shell formulations in the world, and I know his work is fantastic. But even but if I try to use a very rich discretization of shells to capture such a complex origami behavior, this can take some time. Just generating the mesh, having the right boundary conditions, can take some time. Then we wanted to do something that would maybe not be as accurate as JN shells model, certainly not, because we are going to simplify, but would be very efficient, would allow us to do many simulations in a few minutes, okay? Then I want to consider, for example, panel shear and the stretch, and this I am going to use bar elements. and also the panel bending. And then I am going to use a rotational hinge to represent that, and also the fold bending. And most rigid models, they only consider this one. And here I will also use a rotational hinge to represent that. And here is the literature. It started these simplified models with Schenck and Guest. And then we extended this, as you can see. And lastly, I am going to talk about it. We also extended it to finite deformations and nonlinear mechanics. And then the key idea is that, for example, if we can develop the stiffness matrices in each case, as you can see, and then we can form the stiffness matrix with contributions from each case. And but I said we want to understand the origami through mechanics. Most of the literature is concentrated on rigid folding. That is the one like this. But however, for example, if you want to bend the origami, that's impossible to do it with rigid folding. We need to consider non-rigid. And then this is the key idea. And now we have to introduce finite elements and nonlinearity. And here are the best references, the one I learned the topic, and the one that we are going to use now, the nonlinear FEM, in order to do the nonlinear mechanics of non-rigid origami. Thanks, JN, for your excellent books. And actually, when I learned FEM, JN did not know that he was helping me, because at that time I was a student in Brazil, but I learned from his writings. Thank you. So, and the key idea here is to have just two basic elements. We are going to use hyperelastic constitutive laws. Then I do one derivative of the strain energy function, get the stress, another derivative, get the modulus. But then this will be just 1D because it's just 1D bar element. And then I can do the FEM formulation and incorporate both material and geometric nonlinearity, as you can see here. And something very interesting in the origami is that we need to consider finite rotations from 0 until 2 pi, because the origami can fold in itself, right? 0 configurations like this, 2 pi is like this, but they are totally different, and we have to go everywhere in between. Then for the moment rotation relation, we also use another type of strain energy function, so that when we do derivatives, we can get the moments and the stiffness. And when we get close to 0 and close to 2 pi, in order to avoid the sophisticated contact algorithms, then we have a simplified way where we consider barrier functions, so that there is a very large barrier at each endpoint, so that we can avoid the contact. So we can avoid only here we only take care of the local contact, and that's what we were interested. And then this allows us to have enough information to build our internal forces and our stiffness matrices for the system. And we have to have also a unique way, since now the deformation is really finite, especially rotations, that we have to go from small rotations all the way until 360. And this configuration is very different from that one. The point here is that we have to have a unique way to define the angles, and we can achieve that with this red line approach there. Okay. One remark that is important is that I have been working with finite deformations, but in general, we have trigonometric functions. When we do derivatives, use the chain rule, then we are going to have trigonometric functions in the denominator. And this can be a serious problem because we can get singularities. The limit might be finite in this expression, but the computer, the algorithm, may not know that. So this was creating too much problem. What we did was to use vector and tensor functions and rewrite, manipulate, do some tensor algebra to rewrite these expressions, so that all of them, the first order derivatives and the second order derivatives, the Hessians that we need, they would not involve any trigonometric functions, as you can see here. And this allows us also to complete second order information, and then we can get all the derivatives that we need without any trigonometric functions, just with distance functions, vectors, and tensors. And that's the key idea in Merlin. And regarding the solver, we use a modified version of the arc length that is a modified generalized displacement control method. And I was going to give a live demonstration here to show Merlin, but in the interest of time, I decided not to. This is highly nonlinear problem. And what I am doing here, if you can see, is a pop-through defect. For example, I am going to apply a load here, and then you can see that there is a defect here, okay? And then this is a problem that involves a snap through, a snap back, and then all these plots were obtained from Merlin, and you can download it from my website. And then at the end, for example, you can get the energy that you are going to get in each of the 3 modes that we approximated, the stretch, the bending, and the folding. Okay. All right, and as I said, I will not do the demo of Merlin in the interest of time, but you can download the software from my website. And now let's take a look what we can do with these origami elements. And let's take a look, for example, at a Miura strip, and let's look at its eigenvalue versus extension when I get the strip, and I look at the extension of the strip, okay? And here on the left, I start counting from 7 because the first 6 are rigid body modes. And you can see that if I look at a sheet, then this is not very exciting. I was trying to look at the band gap here, and the band gap is pretty small. And then we looked at a tube, and now it's a little bit better, but the band gap is really small. And then we looked at different configurations, like aligning tubes and having an internal couple of tubes. This was suggested by Schenk and Guest, or doing the new one, the one that we proposed, that is the zipper coupling. And the zipper is that one, the big one. This is the zipper, all right? This is the zipper. Okay. Now, as you can see, for the tube, the aligned tubes and the internal cannot extend all the way because the internal, the blue tube inside it will lock the system. But you can see the band gap I am looking is not that exciting because it's not that big. They all seem similar. But look at this. When we do the zipper, this is quite exciting because now you can see that the first mode, right, is a very low stiffness mode, near zero energy mode, very low stiffness, and all modes are, all other modes, bending, twist, combinations, they are much, much higher, and maybe even order of magnitude higher than the first mode. So this is quite exciting, and I will not have time to go through all the details in this work, but this work was published in PNAS, the reference is here, and you can find all the details there. And if you have any question, I'll be glad to talk to you. I'll just give one explanation why this works. We use Merlin to do the analysis, and I will just concentrate on the zipper. You see what happened here is that, let's say the first non-zero modes, then you can see that almost all the energy is in folding, very little in bending, and that's what you want, right? That's a mechanism, that's what you want. And you can see that all the higher order modes, then they are mobilizing a lot of shear. You see a lot of green here and a lot of bending. And then if you look here, the first mode, that's our mode, that's the mechanistic mode, that's the deployment mode, that's the mechanism that we want. Almost all the energy is here, is in folding, that's what we want. And all the higher order modes, you see, all the energies are distributed more or less in bending and shear. And this is what allows this system to function, to work so well. We skip this. What can we do with this? For example, we can assemble them in different ways to create cellular assemblages, and with origami, we can also benefit from aspects of self-assembly, deployability, tunability, and so on. And here is a metamaterial that we created that has aligned tubes in one direction and zipper in the other direction. And here is a prototype of, on my hands, of this metamaterial. As you can see, it is flat foldable in 2 different directions, this one and this one. Probably the video does not allow you to see very well, and is very stiff in the Z direction. And it's very exciting. For example, look at the X and Y. When you compress in one direction, you compress in all the other directions, then it's very clear that the X and Y is an auxetic plane. And then if you look here at the stiffness versus extension, in all the directions, you see that it's quite exciting. The Z is very stiff, but the X and Y directions, they can extend all the way from 0 to 100, and they are much more flexible. And you can see that, and then, for example, you can have an infinite number of metamaterials here, configurational metamaterials. You can just choose an extension and freeze that, and then get your metamaterial and see how it behaves. And another interesting point is that you have an instability point there. This happens when all these panels, they align, and then the origami has to decide if it will go left, as you can see, or right, okay? That's the reason of that instability point. And then, as I said, you can freeze one of those infinite number of configurations, choose one, and then you can do your metamaterial and see how it behaves. What else can we do with this? For example, we can arrange them in, we can be creative here and arrange them, for example, in different ways, like in this interlocking pattern. This looks like could be like a building kind of idea, right? That has two scales, the global scale and then the cellular scale. Or here, you can even do a bridge type of structure that this was made of paper, but is quite strong, as you can see. All right, but can we do this at the material level? What about doing this at the micro nano scale? And that naturally leads to the topic of the micro scale origami architected metamaterials exhibiting macro scale reversible auxeticity. There's a reversible auxetic behavior that I will explain. And here you can see, if you look at the scale, see, this is quite big. That one is huge, right? I have several orders of magnitude here. That zipper is huge. This one is on my hands. And this one is just 30 microns. Take a look here on the scale. I am circling it. You can see, right? 30 microns. All right, if I look in the literature, most of the works, they only do a unit cell, for example, kind of like this one, or they try to do very simple assemblies, okay? And then when it becomes more complex, then it becomes bigger. But we wanted to do the metamaterial, and then you can see here comparing, you can see the dimensions of the features of our metamaterial. And you can see here the dimensions in the literature, and ours is about the panel dimensions about 13 microns. And to our knowledge, for an origami metamaterial, origami, not lattice, origami metamaterial, this, to our knowledge, this is probably the smallest we have seen. And then we can do a rigid origami model to work the kinematics. And we did this by means of a 2-photon lithography using direct laser writing and used a nanoscribe machine. And all the experiments were done in the SEM, as you can see here. And then we investigated a few properties. I will not have time to go through all the interesting properties that were found, but I will highlight just a few ones. In this micro nano scale, it's very interesting that the system is highly anisotropic. As you can see here, each direction has very different stiffness, and this can give a lot of freedom in the design. Another very interesting aspect is that if here, well, this is a viscoelastic material, we are using a polymeric type of resin here. And you can see that then we modulate this, the loading. We modulate, load, modulate, load until we reach the desired level. And then you can see here that this has more or less linear elastic and a plateau type of behavior. And here are the states in each case, 1, 2, 3, until 7. 7 is the final one. What is very interesting is that this has a lot of recoverability properties. If we wait about half an hour after we reach 7, then we almost go back to 1. And then we can repeat this. Here is another direction. And now you can see clearly this is a hardening type behavior. And again, we can see the recoverability property that I have mentioned before. And the Z direction is quite interesting. And this one, we did some block wave analysis that Professor Lim already explained, so I don't need to explain. And then we could capture a global instability mode, and later a cascade. After the global, there is a cascading instability mode, global and local. in the interest of time, I will skip the animation. And another aspect that was fascinating was the auxetic behavior. What we noticed is that we did some analytical derivations for the Poisson ratio. And then in the z direction, the xz should be 0 if we do a rigid origami. Of course, it will not be 0 if we do experiments because the material will deform. But considering a rigid origami model, that's what we get. And there is a sweet spot around here. Okay, here is just a zoom of the curve here of the angle psi, that is this angle versus the Poisson ratio. And then we can see that on the yellow region, I have a positive one, and on the negative, on the green region, a negative one. And the question is, can we capture this experimentally? And the answer is yes, we were able to capture this change of Poisson ratio. And here are some illustrations of the Poisson ratio in the x and y that is negative, and the z that should be 0, but experimentally cannot be 0, but it's close to 0. And here is the verification of the Poisson ratio switch going from positive to negative. And all the details of this work are in this paper that was published in the journal Small. And this is the cover of the journal when the paper was published. Finally, my final topic is I would like to talk now about robots, about untethered origami robots using distributed actuation. Okay. And I feel that the topic, also JN asked me to say my vision, what comes next. I feel that the topic of origami robotics will be really transformative. And I think this has a great potential in many different fields. Space exploration is one, but one that we really like is in the medical field, because these origami robots, for example, they could be used for things in the future, like drug delivery, for example. And that's something that we are working on right now. It's not part of this talk, but that's what we are working on right now. A big problem in origami is actuation. As you have seen here, my actuator in my talk were my hands, right? This is my actuator, as you have seen. This is my actuator. And there are other actuators in the field of origami, but many times they are extremely invasive. They introduce a lot of tethers, control system, and sometimes they even put all that thing huge inside the origami, or they have to change the design, extremely invasive, to put all, maybe sometimes wires, control, power.
Dr. Paulino,
yes.
Dr. Paulino, you have about 10 minutes more, yeah?
Thank you. I will conclude. Thank you very much. And the key idea here was to do something that is really, that can be done fast and on demand and with non-contact. And then we use magnetic actuation. Here is the origami, and this is the magnetic plate. And here is, as you can see, when we apply the magnetic field and we actuate, look how fast it is. You cannot even see, so I will repeat again. I will repeat again for you to pay attention. And now I'll put it 20 times slower. Many times in the literature, they show the actuation with stimulus responsive materials, many times 20 times faster. Here I am making it 20 times slower. And now I will show you here that I really love this pattern. It's called the Kreslin pattern. And this is an exercise that I did in my class. Sometimes I don't know the difference between research and teaching. Since I don't know that difference, we use that in the class. And what I want to show you is that the Kreslin pattern, the one I just showed you, can form spontaneously. And I think this is very beautiful. I will stop sharing the screen because I want to demonstrate that to you. And here is just a cylinder, right? And now pay attention. I put some markers here for the students. Okay, pay attention now. I will just apply a torsion here, okay? And take a look. The Kreslin pattern will form naturally. And this is quite repeatable. Maybe if I do it a second time, it will look better. Yes. Okay. And then, as you can see here, this essentially is the Kreslin pattern. Okay, and all right. So just to move on, then we do the Kreslin design, as you see on the left, and now we consider two states. The Kreslin has bistability, provided that you do the design correctly and use the proper material. Then we can have the state 0, that is the folded one, and the deployed one that we call state 1. Okay, and then we apply the magnetic field, and we have a magnetic disk, and this disk will be magnetized in the direction M here, and then we are going to apply a magnetic field, and then we can see the torque that is generated, that is given by this expression, where V is the volume of the plate. And when we do that, what happens is that the magnetization tends to align with the direction of the magnetic field that is applied. And then, for example, if this is the required torque, if I apply a torque that is given by the blue line, nothing will happen. But if I do the red line, then I will pass this barrier, and then I will change from state 1 to state 0. And here is my design domain of the magnetic field versus the angle of magnetization. Okay. So what is very beautiful about this is that this can, I have been doing this in isolation, but this does not need to be done in isolation. We can combine them, and then we can have here, for example, different states. This can be just a system, for example, for digital computing, and this here, for example, is 0, 0, 1, 0, and this is 1, 1, and then, for example, from the 0, 0, I can go, I can do the design, and I can prove that I can go from any of these other ones, for example. And also, another thing that we wanted to do is to explore the reverse trees. What happened?
5 more minutes, Claudio.
Okay, almost done. What happened is that, let me show this demo here. What happened is all the previous creases, they had the same direction, but this one now has a reverse crease. And this is very interesting because this allows us to explore more interesting behavior and kinematics, okay? All right, and here is the map where, for example, you can see that I go from 0, 0, that is this one, to 1, 0, as you can see here, and from the 1, 0, I go to 1, 1, as you can see here. From the 1, 1, I can go to the 0, 1, and then to the 0, 0. And you can see that I cannot go from 0, 0 to 1, 1, but there is always a path where I can reach there, okay? So these are this is the experimental setup where we did all the tests. And this is my favorite slide. It's a very simple one, but what you see is that I mentioned to you that the system is bistable. And now you can see that, for example, if I just control the height, the green is the short one that has a lower force to activate bistability. And then you go to the blue, the brown, and the red. And now you can see that the bistability now, the mechanics is dictated by this single parameter, the height. Now the geometry became mechanics, mechanics became geometry, because now just by controlling the geometry, I can control the bistable behavior. And moreover, with the guaranteed bistable behavior, I don't need any locking mechanism. The locking mechanism in the system will be given by the bistability. And finally, this is the final point, is that we can do now a multi-physics system, a magneto-mechano-electric origami assembly, and then we can use a Smith trigger, for example, where we can change these states from when I have closed the switches here, the blue one, then this will be in the stable state 0, or when I open the switches to the stable state 1, and then I'll need an electrical system that will be connected to the Smith trigger that will be achieved by this means of copper tapes that will get either in contact or out of contact, depending on the state. And this is the domain map that we get. And here is the video. And this is the final thing I am going to show, where you can see here the controllable switches, the change of the states. And now you can see the micro robot, the magneto-mechano-electrical assembly, where you can see I can change, it's like a system for digital computing, where I can change on demand with distributed actuation independently from going from any state I want almost to any other state, okay? And finally, these are our concluding remarks that you have seen. Origami, I think, is quite pervasive, has lots of applications. Thank you very much. We'll be glad to answer questions.
Thank you so much, Dr. Paulino. I'll open the floor for questions. I think there's a question from Dr. David Bigoni. Dr. Bigoni, can you unmute your... He said his question was too long, so he wants to ask it personally. Yeah?
I want to write a long stuff. Glausio, compliments. That's beautiful talk. Very exciting.
Thank you.
Nice talk. And compliments for the medal. So my question... Do you hear me?
Yes, I can.
Yeah, my question is related to the Kresling effect, which is beautiful, and it's a bifurcation. It starts as a bifurcation under torsion and develops as a sort of localized folding. So I'm wondering if you ever consider the possibility of creating materials where the localization of folding occurs spontaneously instead of occurring at fixed positions. Because usually people doing origami fix the position of the hinges, and in that case, it's not fixed; it is created.
Yes, you mean spontaneous formation like this one?
Yes.
Yeah. Dave, I wish I could answer yes to your question, but that's just my wish. This is something that is intriguing me a lot. It's something that I really want to understand. I am very interested in these spontaneous pattern formations, and this happens a lot in nature, a lot. And even this system here that I just showed you, right, and you can clearly see here, is very repeatable, you know, it's very repeatable and very nice. My answer is quite simple. I am very interested on that. Maybe if you have some ideas, we could collaborate. I don't quite know how to get there, but it would be really fantastic to have a decrease on demand. We could have structural and material systems with properties that would be totally unprecedented. There are some, look, Dave, there are some papers that somehow they do this, but it's in a very predictable fashion. I think it's not what you are asking. Okay, so that's essentially is my answer. I think this is the research of the future, and I am now I am working with a student and a colleague exactly on this topic. Maybe you can join us.
Sure.
I work with Professor Zeb Rocklin and James, and the main topic of our research is to try to understand the spontaneous pattern formation, especially looking at origami systems, control metamaterials, and properties that will arrive from there, not just in static case, but also in dynamic cases, because waves could have a tremendous implications on that behavior.
Thank you, and compliments again.
Thank you so much, Dr. Bigoni. The next question is from Dr. Raj Kota from Texas A&M. Yeah. So, can you, for Dr. Paulino, can you please comment on the effect of fatigue, repeated push or pull of origami structures? Is the life of origami structures primarily material dependent or fold pattern dependent?
I think it's a combination of both. Actually, you asked an excellent question. I don't know if I may not have time to show, but I can tell you that, for example, let me see if I. For example, in this paper that we just did in PNAS. Do you see this plot? This is the supplementary information. And then you can see that this is load versus the displacement. And if you look here, for example, with a repeated loading, then the behavior keeps changing. And that is useless from an engineering point of view. But then what we noticed is that, and that's what I didn't explain it in the interest of time during the presentation, but in all these tests, that's what we do. What we noticed is that if you can see here, around the 400 cycles, 500 cycles, then the behavior stabilizes, and then we can use the system. But this is just for this material system that we used. Now, if we are going to use, for example, like what I showed, the origami metamaterial at the micro nano scale, because there we are using this polymer type of resin, and we need to do a very good characterization there, and to have a very good understanding of the issues that you mentioned, especially, for example, fatigue, cracking, instabilities, and so on. And I feel that there is a lot of room for this to be done. And what happened with the origami is that what happened is this. I said a combination of the factors that you mentioned is that for standard materials, then we have standard procedures for characterization, and now you have the origami. And many times the assembly that you have of the origami, the way you do the joint, the way that you, if the origami is developable or non-developable, or very small details that you change, even the thickness of the material or the connection that you do, the behavior can change completely, okay? And then the ability to do an effective design is, I think, is a great area of research. I think some work has been done, but I think there is a lot more to be done. We must get a better understanding of this. And but that's where we are. But now there are some papers in the literature, even recently, where people are trying to merge the two things: the standard techniques for material characterization with some features of origami behavior. However, there is much more to be done.
Thank you, Dr. Glausco. The next question is from Dr. G. Wang. How about the vibration properties of origami structures? Are there special features that can be utilized?
Excellent question. I would say a lot of what Dr. Lim talked about the dynamics would also apply to origami. And recently, I think it's here, I can show you still like paper. For example, very recently, we wrote this paper here that does exactly what, does not answer you completely, okay? Answers you partially. But this paper here, I don't know if you can read here.
Yeah.
Can someone read for me? Because I cannot read from the book.
Yeah, we can see.
Can you read, please, for me?
Block wave framework for structures with non-local interactions, applications to the design of origami acoustic metamaterials.
Yeah. So then here we addressed the acoustics and the band gap formation, wave propagation, wave tuning, and how we can tailor the waves depending on the origami system, and how to understand the periodic system. But in this work, one of the main contributions was to try to understand from a fundamental level the periodic system. There has not been much done in the field of dynamics and wave propagation in origami, and I think there is a lot to be done. Katia Bertoldi, David's former student, is doing a lot of work on that, and I think Chiara D'Araio is also doing some work. But there is much more to be done.
Thank you. Thank you, Glausco. The final question, in the interest of time, from Dr. Tom Lacey. How tightly can you control the diploid or final state if there are strict requirements on the outer mold line features and surface morphology? Say, for example, cases where the various signatures like EMI or thermal, etc., are critical.
Yeah, this I think is a very deep question. What I can say is only along the lines of the fields that we investigated in terms of multiphysics. We have investigated, as you have seen at the end, the magneto-electromechanical system. And we also did some work in coupling wave propagation to do frequency selective surfaces so that we could we could design FSS, frequency selective surface, or antennas. We could change their resonant frequencies depending on the origami pattern that we had. I have not done much work along those lines, but I think this is a very good point, and this is a very good area for exploration.
Thank you, Glaucio. Since we have a bit more time, we can ask one more question from Dr. Olivier Alex. Could you comment on the progresses regarding applications? Those mechanics are used since long in the aerospace, but also other domains, and what can be expected there on recent progresses of your research? So basically, it's an application-oriented research for future. Yeah?
Yes, I feel that really the field of origami engineering is really an emerging field, and there is a lot to be done. A lot, for example, in terms of applications of the origami concept for space exploration, right? This has always to be used because, for example, a satellite, it has to be compact when you are on Earth, and then we get on space, this has to deploy. And that's what motivated the development of the Miura pattern. That's, he was working for NASA in the 70s, and that's when the pattern was created. And over there, there is a lot of mix between origami and mechanisms and robotics. But now, for example, in terms of applications, as I indicated, I see a lot of applications in the medical field. For example, Professor Dave Gracious at Johns Hopkins is doing some very beautiful work. And in space applications, for example, here in the US, Professor Pellegrino at Caltech is also doing some very interesting work. The applications, I feel that the origami, what happened is this, my personal opinion. Origami seems very attractive and seems very easy, okay? But it's not, there is nothing easy there. It's the most difficult topic I have ever worked in my life, and it's extremely unforgiving. So it's very easy when working with origami to solve meaningless problems, okay? And unfortunately, the literature now is being packed with a huge amount of work because it's attracting lots of people. But I feel that the applications, they are fundamental. We need to work on the translation from the research, from the concepts, from the research, from the academic concepts to real applications. Let's say to first proof of concept applications and then actual applications. And I think this is very exciting because, again, the medical field and also space exploration, Jeff Bezos wants to go to space, Elon Musk, right? Space applications, I think origami has to play a major role. I don't, in my opinion, it's impossible to explore space without origami concepts. That is a must. So.
Thank you so much, Paulino.
Thank you.
Right. With that, we've come to the conclusion of the seminar. So I would like to invite Dr. Reddy again, to provide the brief citation for the two winners and present medal winners to the medal winners.
Okay, thank you, Prakash and Arun, for acting as the hosts of the plenary lectures. I want to thank both C.W. Lim and Glaucio Paulino for excellent, very passionate presentations. So that really should rub on to some of us in terms of how we do things, having the passion, drive. So I also want to thank, before I forget, I tried individually, but thank every one of you, about 75 people logged on. So it is a great to see many of you. I could not see you physically, last year and so, but it's good to at least to see you are here. I like to take now the opportunity to make the presentation of the medals, and we will begin with the in the same order as the presentations with the CW limb. So I will ask the recipient to show the medal to the audience, because that way we all feel that you did receive the medal. So I will begin with a brief statement. I did send you, each of you, in my last reminder, the full, or let me say brief, but summary that is highlights of their career. So C.W. Lim is a professor in the Department of Architecture and Civil Engineering at City University of Hong Kong in mainland China connection, the special region of China. And I know him for a long time from his student days when he was a student in Singapore. Then he went on to do postdoc with Kitty Ponchai, whom I also know very well. I met him there. Then after he moved to Hong Kong, I visited him several times. I collaborated with him. So the two main highlights that he presented, symplectic elasticity and also the metamaterials. And both of them are really significant topics and modern topics. And I'm sure both of those do have quite a bit of work to be done. So I will not read his resume, but just say that he's a co-inventor of two patents on local surface non-crystallization treatment methods and devices. And so he's, of course, a fellow of ASME and also fellow of ASCE, American Society of Civil Engineers, and Engineering Mechanics Division of ASCE, and also Hong Kong Institution of Engineers, which is a we don't see those professional societies in this part of the world, but the UK and Commonwealth countries have the fellowships in the Institution of Engineers, and he's a fellow of that. So in awarding this J.N. Reddy medal, is cited for the significant and original contribution to vibration of plates and shells, smart piezoelectric structures, nanomechanics, and symplectic elasticity. So we all put our hands together, congratulating C.W. Lim. Can you come on screen and show your medal, please?
I
Is
can
there a
see
way
that.
we can highlight him? Okay, good. All right, can you turn it a little bit? Okay, there you go. All right, thank you. Thank you,
Nice.
Siva. We appreciate you taking time and delivering the plenary lecture, and congratulations to you on receiving the medal.
Congratulations.
Congratulations.
Thank you
Congratulations.
very much. It's my appreciation to know you and to learn from you, particularly during my PhD days until today. I learned, in fact, a lot from you. And also, I wish to take this opportunity to thank two groups of my collaborators from Dalian and also from my students. And in particular, the support of my family is tremendous, and I appreciate very much. Without the support from my family, I wouldn't have achieved what I have had today. Thank you very much.
Thank
Oh,
you.
yeah. I
Congratulations.
also have a certificate.
Oh, you did receive it.
No,
Great. I was wondering whether you received it or not.
Yes, yes. Thank you very much.
All right. Thank you. All right. We move on to the next recipient, Professor Garcia Paulino, the Raymond Allen Jones Chair in the Department of Civil and Environmental Engineering at Georgia Tech. So, again, it goes back to a long time from his Cornell days. And I did not meet him at Davis. That's where he started his career as an assistant professor, but I met him many times since then at the University of Illinois, giving several seminars. And then, just before this COVID thing arrested, the last trip I took was to Georgia Tech to give a seminar. So I want to say a few words. And he received his bachelor's degree from University of Brasilia in Brazil in 1988, and a master's and PhD from Cornell. And so his latest move to Georgia Tech, he was given the chair, which I already mentioned. But he has been really very passionate contributor to several topics, including the functionally graded materials. I remember that is the first topic I connected to him. And also then he worked on cohesive zone models. And the latest passion, as you have seen, is his origami structures. So anything he undertakes, he tries to get to the depths of these topics, which is what we admire him for. And he has received many awards. Walter L. Huber Civil Engineering Research Prize from American Society of Civil Engineers, and then several other awards. He's of course a fellow from USACM, US Association of Computational Mechanics, and also American Academy of Mechanics, ASCE, ASME, all of these he's a fellow. Then he received Ted Belichko Applied Mechanics Award from ASME, and in 2015, Cozzarelli Prize from the National Academy of Sciences, and then the 2020 Drucker Medal from the American Society of Mechanical Engineers. And so, of course, the latest prize he has yet to be formally inducted, but it is announced that Glaucio Paulino is elected to the National Academy of Engineering of the United States.
Congratulations.
So congratulations, Glaucio. We are very proud of you, as I am with Chiva. All my friends are very, very affectionate and caring. So that is how I connect, including the two hosts today. So, and many in the audience, actually. I think that's how I connect, not only just through research, but personal feelings for each other. So, last year is recognized for his contributions to in the theoretical and computational mechanics, leading to advances in mimetic-inspired methods, virtual element method, topology optimization, and geometric mechanics associated with origami engineering, including the configurational metamaterials and reconfigurable structural systems. And once again, congratulations, Glaucio. Now you can show your medal much more closer than you did it before. I can't shake hand, but we can put the hand up.
Yes, it's a beautiful medal.
All right, maybe you can show the other side also if you want.
Oh, yes, you can. Let's see if it will be.
There you go.
Very good. All right. And I'm sure, Chiva, you can do the same. I did tell you in my communication, get it inscribed on the medal so that nobody steals it, right?
This is the other side.
Oh,
The
yeah.
front
Okay, good. Thank
and
you.
the back.
All
Thank
right.
you.
So I once again I congratulate each of you, and of course I know you have a tremendous support of not only friends and people like me, but also family. And we wish both of you a bright professional future as well as a life full of joy and happiness.
Thank you. JM, can I say a few words?
Oh yeah, you are allowed to say whatever you want.
Thank you very much. And here again is the certificate. Getting the Reddy medal has been a blessing for me, and I am honored and humbled to get that. And JN, when you announced that I was elected to the National Academy of Engineering, all that I was thinking is I am in very good company because you were the role model for me. And I just picked up a few books on my shelf, and you may like this, JN. Do you remember this one?
Yes.
When I visited Texas A&M, in 2015. And these are books that whenever I teach class in continuum mechanics, I use. And another very nice one. I may have more, Jan, but I just picked up. I didn't plan.
Randomly.
And,
Yeah, it looks like you know, the audience might think I must have paid you some money to advertise my books. Okay.
natural.
That's
Was not
not the
planned.
case.
And
I-
finally, this is very. Finally, I also wanted to say that, as I said, first of all, this is a blessing to get the medal, and I would like to also acknowledge everyone that contributed to this, all the students, postdocs, you know, and also my family, the close family, the extended family, wife, daughter, grandkids, and siblings, parents, everyone. Thank you. And finally, this is very big, and I just want to demonstrate how small it can become, and that's it, I am done. Not so big anymore.
Okay,
Not so big.
put it in your briefcase.
Thank you. Yes, that's what I do. Exactly what I do.
All right. Okay, so anything more from the host? Arun,
I think that's about it, Jan.
I think that's about it. Thank you very much. It was a.
Thank you very much.
Right,
It is really wonderful.
very nicely organized. All the credit goes to Dr. Rajikota, Arun Srinivasa, and Prakash Tamuraja.
Yes,
Thank you.
Raj and Prakash really did the bulk of the work. I was just mostly talking, but it was a wonderful opportunity to share these ideas, and I think it's a wonderful thing to see. I mean, I learned a lot from the talk, so it was very nice. You know, with that, I think we are done. Have a pleasant.
Thank all the audience, about 75.
Thank you so
of you.
much.
And thank you. Some of you, I mean, depending upon time zone, you all worked on different time zones to make this a success. And that is very, very important. And I hope that we continue. You know, the passion for mechanics was very evident from both the speakers and the audience. The questions were very, very nice. So I think that's something that we want to keep as a vibrant mechanics community. Thank you.
Thank you.
Thank you. Bye.
Bye-bye, everyone.
All right, take
Bye.
care.
Bye.
Bye.
Bye, everyone.
Bye.
Bye.
Bye, everyone.
Goodbye.
Bye.
Bye.